All right, today we'll go over the first half of chapter 10, chemical bonding. The outline of what we'll be going over in this chapter is we'll be looking at bonding theories, then the Lewis dot structure. We'll be looking at the Lewis dot structure of atoms, of ionic compounds, and of covalent compounds. Then we'll be looking at the geometries of our different molecules. We'll be looking at the electron group geometry, or sometimes known as the electron domain geometry, and we'll be looking at the molecular geometry. Then we'll be studying briefly electronegativity of our different atoms and how that helps us, along with the geometries, to determine if our molecules are polar or nonpolar. Let us see an example of why understanding the geometries or the shapes of models is important. In 1889, researchers discovered the structure of HIV protease, which is a protein synthesized by the human immunodeficiency virus, which we know as HIV. And that's what allows HIV to copy itself, which is what causes AIDS. So researchers use what is known as bonding theories. That is, they have models online or on the computer that predict how atoms will bond together in order to form certain structures and how these structures will interact with each other. While using these bonding theories, they are able to stimulate how potential drug molecules will interact with that HIV protease molecule. What we see in this image below is that the gold colored structure on the computer is a representation of that HIV protease. And the molecule shown in the center is that protease inhibitor that they found. So using those bonding models, drug companies were able to design a model that would disable protease by sticking to the working part of the molecule, which we call the binding site or the active site. So by the early 1900s or 1990s, several drug molecules were developed that inhibit the action of these HIV protease molecules, and these were called the protease inhibitors. All right, so what do bonding theories do exactly? Well, bonding theories will predict how atoms bond together to form compounds. They also predict what combinations of atoms will form compounds and what combinations do not form compounds. They will predict why salt ends up being represented as NaCl, that is one sodium ion for every one chloride ion, and not NaCl2, that is not one sodium for every two chloride ions. And why water is represented by H2O and not H3O. So these bonding theories explain the shapes of molecules, which in turn determine many other physical and chemical properties that we see. So a lot of what we'll discuss in today's lecture is the Lewis theory. Lewis was actually a scientist that led to what we know as the Lewis structures. In this Lewis theory, we use the valence electrons of main group elements, which we represent as dots surrounding the symbol of the element. So for example, hydrogen, we know, has one valence electron. So that one valence electron will represent with one dot. So the result ends up being what we call the Lewis structure, or sometimes the Lewis dot structure. We have to remember that the number of valence electrons from any main group elements, aside from helium, which has 2 valence electrons, but it is in group 8A, is usually equal to the group number of the element, or will be equal to the group number of the element. So for example, oxygen, if we look at the periodic table, it's located in the group 6A. Therefore, we know that oxygen by itself has 6 valence electrons. The way we draw the valence electrons is we will separate these into 4 different groups. So now we've drawn 1, 2, 3, 4 valence electrons, and after that they start pairing up. So that's 5 and 6 valence electrons for oxygen. So if we look at oxygen one more time, we can see that oxygen is in group 6. This is group 1, group 2. So lithium is in group 1, then beryllium is in group 2, boron is in group 3, carbon is in group 4, nitrogen is in group 5, and oxygen is in group 6. Therefore, we know that there will be 6 valence electrons around oxygen. Again, we have to start drawing the valence electrons one at a time. 1, 2, 3, 4. Then we start pairing them up, 1 or 5 here and 6 valence electrons. We could also see this by writing out the electron dot or the electron configuration. The full electron configuration for oxygen is 1s2, 2s2, 2p6. We only need to look at the valence electrons to see which electrons we need to draw in our Lewis dot structure. Notice that our halogens, our group 8, have a full octet already. 1, 2, 3, 4, 5, 6, 7, 8 electrons. This octet is the most stable of our different Lewis structures. Right? Let us try an example problem. We want to draw the following elements with their valence electron dots. For this, we need to determine how many valence electrons each of our elements have, and then we need to draw their element sign with the different valence electrons around them. Remember that we draw each one individually, and then we start pairing them up into a total of 4 different groups. I recommend pausing the video here and trying this out for yourself. All right, let's do this together. We have sodium. Now there are different ways to determine how many valence electrons sodium has. One is by writing out its electron configuration. So I will write the condensed noble gas configuration for sodium. So the nearest noble gas was neon. And after that, we start our valence shell, which is our 3s. And for sodium, it is 3s1. So what we see is that we have 1 valence electron for sodium. So for sodium, we draw its elemental symbol, and then we draw just that 1 valence electron. All right, let's try for number 2, magnesium. For magnesium, let's write out its condensed noble gas configuration. So we have neon, and then we have 3s2. So that means that we have 2 valence electrons for magnesium. So we'll write out the elemental symbol, Mg, and then we'll draw one electron here. And remember, we don't want to pair up this electron until we have to, and so we'll have another electron here. So that is the elemental Lewis structure for magnesium. Let's do the same thing for aluminum. The noble gas configuration is that we have neon. We have the 2 electrons in 3s2, and now we have 1 electron in 3p. So in total, we have 2 plus 1 electron, which equals 3 valence electrons. So for aluminum, its elemental symbol is Al, and then we'll draw the 3 valence electrons, still without pairing them up. For silicon, writing out its noble gas configuration, we have that the noble gas is neon, then 3s2, 3p2. Let's take these numbers that represent the electrons, the valence shell electrons, add these up, and we see that we have 4 valence electrons. So silicon's symbol is Si, and now let's draw our electrons around it. All right, lastly, for phosphorus, its noble gas, or nearest noble fulfilled noble gas, is neon. Then we have 2 electrons in 3s2, and we end up with 3 electrons in the 3p orbital. So in total, we have 2 plus 3 valence electrons, which means that we have a total of 5 valence electrons. So the symbol for phosphorus is P. And let's start drawing our electrons around. First, we want to draw them without pairing them up. So we have 1 here, 2, 3, 4. And then for our 5th electron, we now need to start pairing up our electrons. So our 5th electron is now going to be paired up. And that will be your Lewis dot structure for phosphorus. Now helium is one of our exceptions because its electron configuration and the Lewis dot structure have 2 electrons exactly. Remember that the 1s, or the n equals 1, can only hold 2 electrons. So for helium, its Lewis dot structure contains 2 paired dots, and we consider this a duet. So for helium, we are not looking for an octet, we are looking for a duet. And that will represent the stable electron configuration for helium. So in the Lewis dot structure, or in the Lewis theory, it says that a chemical bond will involve the sharing or the transferring of electrons to attain the stable electron configurations for the bonding atoms. So when we're looking at ionic bonds, here we see that the electrons are actually transferred from one atom to the other. If we're looking at a covalent bond to form a molecule, we see that the electrons here are actually shared. In either case, the bonding atoms will attain a stable electron configuration. So a stable configuration usually consists of 8 electrons in the outermost or the valence shell. This observation leads us to see that most atoms will want to follow the octet rule. So that is that in chemical bonding, atoms will share or transfer electrons to get an outer shell that will have a total of 8 electrons. Again, there are some exceptions. Helium, we saw, by itself follows a duet. When we do have these compounds or molecules, we also see that there's a few other atoms or elements that also do not follow the octet rule. These are hydrogen, lithium, and the beryllium elements. So each of these elements will achieve stability when it has just 2 electrons, or what we know as a duet of electrons in its outermost shell. So we saw earlier that for ionic compounds, the electrons are actually transferred from one atom to the other. We know that ionic compounds occur when we have a metal bonded with a nonmetal. And we see here that the electrons are transferred from the metal to the nonmetal. So the metal becomes our cation, and the nonmetal becomes our anion. The attraction between the cation and the anion will result in what we know as the ionic compound. So let's look at an example of elements that form an ionic compound. So if we have a potassium element, which is shown here, and we also have a chlorine element, which is shown here, we know that potassium has 1 valence electron, so we represent that with a 1 dot structure. And for chlorine, we know that it has a total of 7 valence electrons. So it has a total of 1, 2, 3, 4, 5, 6, 7 electrons in its Lewis dot structure. Well, when these two elements actually form an ionic compound, we see that the metal, which is our potassium here, will actually transfer its electron over to chlorine. And it'll fill that empty space here for chlorine in order for chlorine to now have a full octet. So at the end, we see that now potassium has lost an electron. If it lost an electron, we now have a plus state. And because chlorine gained an electron, it now has a minus state because every electron is a negative charge. If we look at the ionic compound that's formed between magnesium and oxygen, magnesium is our metal here, and oxygen is our nonmetal. Magnesium has 2 valence electrons, so we represent that by 1 and 2 valence electrons. Remember, we do not pair them up until we have to. So for oxygen, oxygen has 6 valence electrons. So that is that we have 1, 2, 3, 4, 5, 6 valence electrons around oxygen. And this metal will give up its electrons to give oxygen its full octet. So oxygen needs, at this time, 2 electrons to have a full octet. And magnesium has those 2 electrons to give to make that full octet around oxygen. By donating those 2 electrons to oxygen, magnesium now has a positive charge, specifically a 2+ charge because it lost 2 electrons. And because oxygen gained 2 electrons, it now has a 2- charge. If we look at the ionic compound that's formed between sodium and sulfur, here we see that sulfur, like oxygen, needs 2 more valence electrons in order to form an octet. Each sodium only has 1 valence electron to donate towards sulfur. Therefore, we need 2 of these sodium elements to donate its electron to form an octet around the sulfur. So each of the sodiums are going to lose one electron. It only has one electron to lose. And it will form an Na plus charge. So we will need 2 of our sodiums to form that positive charge. And with both of our sodiums giving 1 valence electron each to our sulfur, we now have a sulfur with a full octet. And now that sulfur gained 2 electrons, so it has a 2 minus charge. Notice that we draw the cations on opposite ends of each other, because we know that positive and positive charges actually repel, and positive and negative charges attract. So this positive charge is attracting to the negative charge, and this positive charge is also attracting to the negative charge here. All right, let's try our next example problem. Do pause as you try to work this out for yourself. Here we want to draw the Lewis structure for each ionic compound. So the first thing we want to do is we want to see how many electrons each of our elements have in its valence of its valence electrons. So for sodium, it has 1 valence electron. For fluorine, it has a total of 1, 2, 3, 4, 5, 6, 7, as do all of our halogens. We know that fluorine needs 1 more valence electron in order to form an octet, and sodium has that 1 valence electron that it will donate. So the ionic compound that is formed is that sodium gives up its electron, and when you give up electron, you gain a positive charge. And the fluorine, so the negative charge, or for our anions, we always draw those in square brackets. Our fluorine now has a full octet, and we represent its charge outside of the brackets. All right, let's do the same thing for calcium and for oxygen before they've actually formed the ionic compound. So calcium, from the periodic table, we can see that it has a total of 2 valence electrons. Our oxygen has a total of 6 valence electrons. So that's 1, 2, 3, 4, 5, 6. We see that oxygen needs 2 more valence electrons in order to have an octet. And calcium is going to give up its 2 valence electrons. So we form calcium. After it's donated both of its valence electrons, we now have a 2 plus charge. And oxygen, which gained the 2 electrons, has now an octet. Remember that we need to write the charge of the anion outside of the square brackets, and we have a 2 minus charge. For ionic compounds, remember that the charges overall at the end need to cancel out. So a 2 plus and a 2 minus equals a 0 charge at the end. All right, let's try the same thing for strontium bromide. Strontium, the element by itself, has 2 valence electrons. Our bromine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, and 7. We see here that we will need 2 of our bromines in order to form our ionic compound here. So when forming strontium bromide, we see that each of our bromines only needs one more valence electron, but strontium is going to give up both of its valence electrons. So we will have each of our bromines achieving an octet after it gains one of those valence electrons from strontium. It's with the minus charge. So now strontium has lost one of its valence electrons, but it wants to lose both valence electrons. So we need another bromine, which gains one valence electron in order to achieve an octet. And at the end, we have strontium that's lost both of these valence electrons now. And if it's lost both of these valence electrons, it now has a 2+ charge. Again, the charges should be equal to 0 if you sum all these charges up at the end. A -1 charge plus 2 minus 1 equals 0. Notice that I wrote our negative here, or one of our anions here, which is attracted to our cation, and the other anion is also attracted to our cation. But our anions repel each other, so they are not drawn close to each other. All right, let's do something similar for our potassium oxide. We have our potassium, which has one valence electron, and we have oxygen, which has 1, 2, 3, 4, 5, 6 valence electrons. Here we see we're going to need 2 potassiums because oxygen here is missing 2 electrons from being a complete octet. Each potassium only has 1 electron to give. In order to have those 2 electrons be donated to oxygen, we need to have 2 potassiums in order for them to each donate 1 valence electron. So it will form a potassium plus after each of our potassiums has given up their 1 valence electron. So we'll have a potassium plus here, we'll have a potassium plus here, and in the center we'll have our anion, which is our oxygen, which now has a full octet after both of the potassiums have donated 1 electron. Oxygen, because it gained 2 electrons, it now has a 2- charge. So we learned about ionic compounds, which form between a metal and a nonmetal, in which the metal will donate 1 or 2 electrons, or 1 or more electrons, and the nonmetal will accept those electrons. We can also have covalent bonds form, and that's what makes up a molecule. Those happen when a nonmetal or nonmetals bond with other nonmetals. And the result is that we have a molecular compound. So these molecular compounds contain covalent bonds in which these electrons are shared between atoms, not just given up or accepted by an atom. So in Lewis theory, we'll represent the covalent bonding by allowing the neighboring atoms to share some of their valence electrons in order to attain octets, or in the case for oxygen, in order for it to attain a duet. So these Lewis diagrams are a set of rules that will be used to help draw a three-dimensional diagram of a molecule on a two-dimensional paper. So let's look at the formation of water, or the covalent bonding between hydrogen, the two hydrogen atoms, and the oxygen atom in order to form the H2O molecule. So each of our hydrogen atoms comes with one valence electron. Our oxygen atom comes with 6 valence electrons. Again, we said that most of our elements want to obtain an octet at the end. So oxygen needs 2 more electrons, and hydrogen will want to attain a duet. So each hydrogen needs 1 more electron. Remember that when we have covalent bonds, we do not have the electrons simply being shared. Simply being donated or accepted. Here, the electrons will be shared. So because oxygen needs 2 electrons, each electron that oxygen needs, or each time that oxygen needs an electron, it'll actually form a bond with hydrogen, which also needs another electron. So we represent that by having these 2 electron dots between the hydrogen and the oxygen. One came from the oxygen, as we see here, and the other electron is coming from the hydrogen, which we see here. On the other side, we see that we now have the other electron that was needed for oxygen to obtain an octet that's coming from this hydrogen. So this hydrogen is also now happy because it has a full duet. Any of the electrons that are not actually being shared between the 2 atoms, these are called our lone pairs. So we have one lone pair here of electrons, and we have a second lone pair of electrons for oxygen there. For our halogens forming a molecule, for example, if we have 2 chlorine elements coming together to form the chlorine molecule, each chlorine element comes with 7 electrons, valence shell electrons, and they are 1 away from having an octet. So what happens is that each one of our chlorines will share that 1 electron that it had. So this electron, the lone electron here, we can represent by this electron here. And this electron here is represented by this electron here. By sharing these 2 electrons, we can now form a single bond that actually is shared between our 2 chlorine atoms, and it forms a molecule now. These 2 electrons we can also represent in a bond straight line, and each time we have a bond that's represented by a straight line, each bond represents 2 electrons. So that is these 2 electrons that are shown here. Whenever we have multiple bonds, they represent more electrons. Each time we have a bond, it represents 2 electrons. So we said for a single bond, say between atoms X and Y, that represents 1, 2 electrons. A double bond between X and Y will represent 2 electrons in each one of our bonds. So that's 1, 2, 3, and 4. So we have a total of 4 electrons here. And if we have a triple bond between our elements X and Y, or atoms X and Y, we have 1, 2 in our first bond, 3, 4 in our second bond, and 5, 6 in our third bond. What we see is that multiple bonds end up being stronger than the single bond. And these multiple bonds end up being shorter than the single bond as well. That's because they end up having less distance between the atomic nuclei. So when we're forming a compound, or I'm sorry, a molecule of 2 oxygen atoms, each oxygen atom comes with 6 valence electrons. If we were to form just a single bond between these 2 oxygen atoms, we would have an octet for one of these oxygen atoms, but for the other oxygen atom, we would not have an octet yet. So what would have to happen is that another one of these lone pairs has to be given or shared to form a second bond. So in total, we have 2 bonds here. So we have a double bond, which is also shown here. This is where our first set of 2 electrons are shared, and our second set of 2 electrons are shared. So we have a double bond here. For nitrogen, we see something similar, except that they will only form a true octet around both nitrogen atoms if they actually have a triple bond between them, which is shown here by lines which each represent 2 electrons. So in drawing the Lewis structures, we will need to count the total valence electrons. So we'll need to count the number of valence electrons that are coming from each element. And if there's a charge on our molecule, as there are for a lot of our polyatomic ions, we'll need to add 1 electron for each of our negative charges, and we'll need to subtract 1 electron for each of our positive charges. After we know the number of valence electrons, we'll need to select our central atom, and then we'll need to write out the terminal atoms around our central atom using first a single bond. If we haven't used up all our valence electrons and we still don't have an octet yet, everywhere that requires an octet, then we need to use consider more than just a single bond. So let's look at an example of where we're drawing out the Lewis diagram for a molecule. So for NH3. For NH3, the first thing we need to do is count the total number of valence electrons. Each nitrogen has 5 valence electrons, and each hydrogen has 3 valence electrons. There is a typo here. We know that we have 1 nitrogen in our compound, but we see that we have 3 hydrogens in our compound. So this number here should actually be a 3. So 3 times 1, so 3 hydrogen atoms, each contributing 1 valence electron, gives us 3 overall valence electrons coming from the hydrogen portion. So 5 valence electrons plus 3 valence electrons equals 8 valence electrons. Notice that our molecule here has no overall charge, so we don't need to add or subtract any valence electrons here. Next, we need to determine what is our central atom, what we'll notice is that we need to place the least electronegative atom in our center. But there are some exceptions. One of those exceptions is that hydrogen cannot be at the center. So if we look at this electronegativity chart, we need to compare the electronegativity of hydrogen to the electronegativity of nitrogen. We see that the least electronegative of these two is actually hydrogen. But hydrogen can only form up to one bond because hydrogen can only have up to a duet. So it cannot be the center atom. So in this case, our nitrogen would have to be our center atom because it can form at least two bonds. In this case, we know that nitrogen is our central atom, and we have 3 hydrogen terminal atoms. So the next thing we do is we draw 3 single bonds to our hydrogen atoms. So that's where we left off, was where we drew a tentative diagram by joining the terminal atoms to the central atom by single bonds. So that's where we have our central atom is nitrogen, and we have single bonds to our terminal atoms. A single bond to a hydrogen here, a single bond to a hydrogen here, and a single bond to a hydrogen here. We saw earlier that we have a total of 8 valence electrons for our NH3 molecule. Now we need to see how many of our valence electrons we've actually drawn out. For each of our bonds, we have 1, 2 valence electrons, 3, 4, 5, 6. So far, we've only drawn out 6 valence electrons. So if we still have more valence electrons to draw, and if all of our terminal atoms are already happy because they have either their octet or the duet, depending on which atom it is, then those remaining valence electrons will need to go on our central atom. So in this case, we have our nitrogen single bonded to each of our hydrogens. Each of our hydrogens is already happy because it has its duet. Because we still have our 2 valence electrons left to draw, we'll now put those valence electrons on our central atom. And now we see that our central atom is now obeying the octet rule because we have 1, 2, 3, 4, 5, 6, 7, 8 electrons around our nitrogen, which did need an octet. If in the case that our central atom didn't obey the octet rule, then we would need to bring the unpaired electrons in from the terminal atoms to make a double or a triple bond. So let's look at another Lewis structure. Here we want to draw the Lewis structure for CO2. So the first thing we want to do is determine which is going to be our central atom. We have our carbon here and our oxygen here. We want to look for the one that's least electronegative, which is our carbon. So we'll draw our carbon in the center and our oxygens on the outside of that carbon. Next thing, we need to calculate the total number of valence electrons that's coming from each of our atoms. So from our 1 carbon atom, there are 4 valence electrons. And from each of our oxygen atoms, we have 6 valence electrons. But we have 2 oxygen atoms, so we have a total of 12 valence electrons that are coming from the oxygens. So 4 plus 12 equals 16. We don't have an overall charge of our CO2, therefore we'll just have our 16 electrons. So remember, the first thing we do around our central atom is we first draw a single bond to our terminal atoms. When we do this, we see that we've only used up 4 of our 16 electrons so far. The next thing we do is we need to fulfill the octet, if we can, around our terminal atoms. So we've already used 14 of the 16 electrons, so we still have the 12 electrons to draw. So we have our 4 electrons around our carbon to our oxygen atoms already drawn in our single bond. Then we draw 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, now we've used up all of our 16 electrons. Both of our terminal atoms are happy because they have that octet, but our central atom is not happy because it requires an octet and it doesn't have the octet. Right now, it only has 4 electrons around it when it wants 8 electrons. So what happens is that each of our oxygens will donate one of its lone pairs to form a bond. So one of these lone pairs will form a bond between the oxygen and carbon here, and one of these bonds for this oxygen will be used to form a bond between the carbon and the oxygen here. So at the end, we see that we actually have a double bond between our carbon and oxygen here, and another double bond between the carbon and oxygen here. We still are using all of our 16 electrons, and we should check that all of our atoms that need an octet actually have an octet. So the oxygen here has 1, 2, 3, 4, 5, 6, 7, 8. So it has an octet. This oxygen here similarly has 1, 2, 3, 4, 5, 6, 7, 8. So it has an octet. And this carbon has 1, 2, 3, 4, 5, 6, 7, 8. So it also has an octet. So this is the structure for our carbon dioxide. We can also represent our bonds by lines. So that is that if we have 2 bonds, or if we have a double bond between the carbon and the oxygen, on the right side, we can represent that by these lines. And the remainder lone pair on the oxygen, or the 2 remainder lone pairs on the oxygen. And on the other side, also represent these 2 bonds by a double bond, and the remainder lone pairs on this oxygen. Now, as we mentioned before, sometimes there can be an overall charge on your molecule. These are known as our polyatomic ions. If we have an overall charge, every time we have a negative charge, that means we have an extra electron. So if we have a negative charge, we'll have to add an electron to our valence electrons. If we have a positive charge, that means that we have actually taken away one of the electrons from our valence electrons. So we'll want to show the Lewis structure for the polyatomic ion within the brackets, and at the end, write the charge of the ion in the upper right corner outside of the brackets. So let's look at an example of one of our polyatomic ions. Here we have our cyanide ion, that's Cn-. The first thing we'll do is write out the skeletal structure. Neither one of these atoms is really a central atom, because a central atom requires there to be at least 2 bonds to 2 terminal atoms. So we just have a carbon atom and a nitrogen atom. Next thing we do is we count up the total number of valence electrons. So we have 4 valence electrons that we can see from our periodic table that's coming from carbon. We have 5 valence electrons that's coming from our nitrogen. And we have an additional 1 minus charge that's coming from that negative charge that's shown for our polyatomic ion. So in total, we have 10 minus, or 10 electrons or valence shell electrons. The next thing we do is we draw the single bond between our 2 atoms first. We see that we've only used up 2 of our 10 valence electrons. The next thing we do is we try to make an octet around our terminal atoms. In this case, both of them can be thought of as terminal atoms. But if we use up all 10 electrons, we see that neither one of our atoms have an octet. So the next thing we do is that we try to use these lone pairs, or some of these lone pairs, to make multiple bonds. At the end, we see that we end up needing a triple bond between our carbon or nitrogen in order to have both of our atoms or both of our elements with an octet state. So in carbon here it has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it, and nitrogen here has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. At the end of a polyatomic ion, we need to have square brackets around our Lewis structure and the overall charge, which is a negative charge here, shown outside of the brackets. Remember that there are some exceptions to the octet rule. We did learn that helium, hydrogen, helium, lithium, beryllium are exceptions to the octet rule. They normally will form a duet around itself. Boron is another one of our exceptions to the octet rule. It normally has only 6 valence electrons. And then in some cases, we have some atoms that in some cases will form an octet, but they're capable of forming atoms or molecules in which they have more than just an octet around themselves. So we see that for sulfur, phosphorus, and really any element that's larger than phosphorus is often able to have any one of our nonmetals larger than phosphorus is able to have a larger shell. So if we were to look at the Lewis structure for NO, we actually see that this one is an exception to the octet rule. What happens here is that NO is actually a radical. That is that not all of our electrons are actually paired up. We see here for nitrogen, we actually have a lone electron. We said before that boron has 6 valence electrons normally around itself when it forms a molecule. So we have 1, 2, 3, 4, 5, 6 electrons around boron. And sulfur and phosphorus can often have more than an octet. So it can have what we call an expanded octet. That means more than 8 valence electrons around itself. So for sulfur here, we see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 valence electrons around sulfur. And the phosphorus here we see in this molecule, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 valence electrons around itself. All right, for our next example problem, let's draw the Lewis dot structures for the following different types of molecules. Remember, the first thing we want to do is we want to count our valence electrons. And the next thing we want to do is we want to determine our central atom, which is normally our least electronegative atom. But we have to make sure that our central atom is able to form more than a duet. So that means that our hydrogens cannot be our central atom. So for pH 3, we see that phosphorus, each phosphorus has 5 valence electrons, and each of our hydrogens has 1 valence electron. So we have a total of 8 valence electrons. Phosphorus has to be our central atom because hydrogen cannot be a central atom, because hydrogen can only have up to a duet of electrons. So phosphorus, next thing we do is we draw single bonds to each of our terminal atoms, and we have 3 hydrogen terminal atoms. So that's a single bond to our hydrogens. We count how many of our valence electrons we've drawn so far. So far we've drawn 1, 2, 3, 4, 5, 6 of our valence electrons. We still have 2 valence electrons left in order to use up our 8 valence electrons. So for our 2, the next thing we would do is we would try to write or draw them around our terminal atoms if they still needed more valence electrons. But in the case of hydrogen, each of our hydrogens is already happy because it already has its duet. So now we draw our 2 remainder valence electrons around our phosphorus. We know that each of our terminal atoms is at a good state, is at the duet that it requires. Next, we need to make sure that the phosphorus has its octet. 1, 2, 3, 4, 5, 6, 7, 8. So phosphorus does have its octet. Let's see for SCl2 how many valence electrons we need. From each of our sulfurs, we have 6 valence electrons. For each of our 2 chlorine atoms, we have 7 valence electrons. So in total, we have 20 valence electrons. We need to determine which of our atoms is going to be our central atom. Here, it's going to be sulfur because it's least electronegative. So we'll draw sulfur in the center here. And first we'll draw a single bond to each of our terminal atoms, which is chlorine. The next thing we do is we draw the remainder of our valence electrons first around our terminal atoms. Right now we've drawn out 4 of our valence electrons, so we have 16 still left to draw. So we have our 1, 2, 3, 4. I need to draw 16 more valence electrons. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we've used up another one of our 12 valence electrons. So we still have 4 valence electrons left. The next thing we do with our remaining valence electrons is if our central atom does not have a full octet yet, we need to draw the lone pairs around the central atom to see if it can have a full octet. So with our 4 valence electrons left, we'll draw 1, 2 for one of our lone pairs, 3, 4 for the other lone pair. So now we've used up all 20 of our valence electrons. And we can see that each one of our atoms is happy because it has a full octet. Next, let's see how many valence electrons we need for F2. Each of our fluorines has 7 valence electrons, so total we have 14 valence electrons. We don't have a central atom, so we just have fluorine to fluorine. First, we'll connect them with a single bond. So far we've used 2 of the valence electrons up. The next thing we do is we need to try to make an octet with the remainder electrons around both of our terminal atoms. So we've drawn 1, 2 valence electrons, or 1, 2 electrons already. 3, 4 electrons. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. In this case, we see that both of our atoms are happy because they already have the octet. And we've used up all of our valence electrons. Lastly, let's look at CH4. Our central atom has to be carbon because hydrogen cannot be. Next, we draw our single bonds to each of our hydrogens. Oh, we forgot. We needed to count how many valence electrons we need. So for our carbon, we have 4. For each of our hydrogens, we have 1 valence electron. So in total, we have 8 valence electrons to draw. Well, by drawing our central atom and a single bond to each of our terminal atoms, we can count now how many of the valence electrons we've used up. We've used up 1, 2, 3, 4, 5, 6, 7, 8 of our valence electrons. So we've already used up all of the valence electrons. Our hydrogens are happy because they only require a duet. And the carbon needs an octet, and it has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. So that is the structure, or the 2D representation of our CH4 molecule. Notice that when you draw some of these Lewis dot structures, you'll notice that we actually have these structures that can be drawn where we have a double bond here and a single bond here, but we could have also happened to draw our single bond here and our double bond here. What happens is that this molecule actually exists in both states. What happens is these electrons that make up this double bond is constantly between these two bonds. So this state is also correct. This is called resonance, when we have these electrons that are constantly between these two bonds. So what happens is that both of these bonds are actually equivalent to each other. So this bond and this bond, which means this bond and this bond, are actually equivalent to each other. They end up being intermediate in strength and length between what we know is the strength and length of a double bond and a single bond. So normally we know that a double bond is stronger than a single bond. Well, in terms of these bonds, these actually come between the strength of the double bond and the single bond. And they're in between the length between a double bond and a single bond. So a double bond is actually shorter than a single bond. And these bonds are actually somewhere in the middle. They're not quite as short as a double bond, but they're not quite as long as a single bond. Here is another one of our molecules that actually has 3 different resonance structures.